Welcome to another week of the Chem 1212 lab here at North Georgia. This week we're going to be taking a look at acid dissociation constants, or calculating an acid dissociation constant in particular for a weak acid. And we are going to be focusing specifically on weak acids when we're talking about these dissociation constants. We'll see why kind of in just a moment. But just to kind of refresh for those of you that haven't got a chance to talk about all of these things yet in lecture, I think most lecture sections should be kind of to this point by the end at least of Monday. And when we talk about weak acids, we're really just talking about acids that don't totally dissociate in water, right? So things that are probably giving off a proton, that's what really makes things acidic, but not quite giving up all the protons that they have. That's going to be a weak acid. So some common examples of weak acids, which for the most part are just anything that's not a strong acid. So this is by no means a comprehensive list. These are just kind of some common ones, right? Like hydrofluoric, acidic, phosphoric, carbonic. These are all weak acids. And really, most of the time for lecture, we'll probably talk about like the 6 or 7 main strong acids that we'll usually ask you to know. And the reason we ask you to know those 6 or 7 strong acids is mainly because if it's not a strong acid, it's a weak acid. And the weak acid list is much, much longer. And so it's easier just to kind of know the strong ones and then know that everything else is a weak acid of some kind. Now, when we talk about kind of acid strength, just something to kind of be aware of, like we have like when we talk about strong acids, which are things that virtually kind of dissociate completely, maybe not entirely, but basically at equilibrium, it's all products, right? Basically H3O plus and A minus. This is, if we give a proton to water, that's where this hydronium cation comes from. This is the conjugate base, and again, I'll go over that terminology here in a moment also. That's also then formed, and this is our original acid, which there's basically none of it left when we reach our kind of equilibrium state for a strong acid. For a weak acid, we get a little bit of dissociation, but not much. And so we see our concentration goes down a little bit for our weak acid itself, but most of what's left at equilibrium is the weak acid. We have a little bit of H3O plus and a little bit of the conjugate base that we end up forming. If we do end up with something that's a very weak acid, which usually at this point it's not even really acidic, these are things that the concentration doesn't even change at all for our weak acid. An H3O plus and A minus, then we basically don't make any of. And so really what we're focusing on here is kind of the middle one, where we have a situation where there's a little bit of dissociation, but it's not very much. Usually just a little tiny bit that's actually going to happen. Now, I mentioned that term conjugate base on that last slide. So if you're not familiar with that terminology yet, how that terminology really works is that most reactions with an acid or a base, if you have an acid, the acid's kind of a proton donor. It's going to lose that proton. Once it loses that proton, what it forms is what we call then the conjugate base. And we call it then that kind of a conjugate acid-base pair between our acid and it's kind of its conjugate base that gets formed. And then likewise, that acid usually reacted with some kind of base that's accepting the proton. So like in our reaction, it's going to be water. Water accepts the proton, and now we form what's called the conjugate acid that's going to pair with the base. So that's kind of where that terminology comes from for things. So when you hear me talking in the lab, kind of as I'm describing things here, here's our weak acid that we're going to be doing. Our base in this case is actually going to be water. It's just going to be our base. And then the conjugate base, and you heard me mention that, that's basically the anion that's left behind from our starting weak acid after it's lost that proton. All right, so the acid dissociation constant itself, this is what we're going to be trying to calculate in lab. It's really just an equilibrium constant. So you will see it typically written as K sub A. It's a capital K with kind of an A subscript. And that A subscript means it's specifically an acid dissociation equilibrium constant. And since it is an equilibrium constant, that means there is a balanced reaction that is specific to these particular dissociation constants. And for all acid dissociation constants, this is kind of the generic reaction that's happening. You have some sort of acid, you're putting it in water, and it reacts to make H3O plus and your conjugate base. That's the generic reaction. So if we're going to calculate an equilibrium constant, right, Ka then is going to be our products. So H3O plus times concentration of A minus, again, coefficients. The nice thing for pretty much all of this, all of your coefficients for all of this stuff are just going to be 1 for the things that we're looking at this week. So that'll kind of keep some of the equilibrium parts themselves a little bit simpler, and that'll actually be the case for a lot of this chapter on acids and bases. But in our case, we have a weak acid, making H2O plus and A minus when we put it in water. Notice water doesn't show up here since water is a pure liquid. It's the solvent in this case if everything's in an aqueous solution. So that's why we don't see water down here anywhere. And then we have our weak acid, our reactant then that's not water, showing up in the denominator here for that the acid dissociation constant in terms of how we calculate it. And in general, the bigger this Ka value is, the stronger the acid is. But since really we look at these Ka values for weak acids, usually what we see is we're going to see values that are fairly tiny, so fairly small equilibrium constants, which is, since you guys have been talking a lot now about equilibrium, and I think everyone's mostly done with the equilibrium chapters, or at least the first equilibrium chapter, small equilibrium constants is usually a good thing because it means we can simplify our math, and we'll see kind of an instance of being able to do that here in a little bit. To give you a perspective on some common Ka values for just some different weak acids, I mentioned hydrofluoric as a common one earlier. See, hydrofluoric here is a Ka of about 3.5 to the minus fourth, acetic about 1.8 to the minus 5. You might see some values, depending on what references you look up for some of these, they might vary a little bit on some of those values. But when we're looking at these dissociation constants, the common theme here for pretty much all of these for the weak acids is that all of these values are relatively small. We see the one here at the top, hydrochloric, that should be one of the ones you recognize as a strong acid, and notice it's very, very large. Right? So strong acids, we expect a very large equilibrium constant here, a Ka value, and oftentimes you won't even see Ka values for those strong acids. You just kind of recognize they're a strong acid and just assume kind of complete dissociation. All the weak ones, we typically need these Ka values for any kind of calculations we usually do. Now, the other thing we're going to kind of talk about that we'll often go over as we're talking about acids and bases is what it means for a solution as a whole to really be acidic or basic. And really, it's all about a relationship between how much H3O plus and hydroxide are really present in a solution. Because if you have one, you're actually always going to have the other. And it turns out like a neutral solution is when your H3O plus and hydroxide are going to be equal to each other. So this would be just kind of water on its own with pretty much nothing else in it. This is kind of what we should see in terms of the H3O plus and OH minus concentrations. If we have more H3O plus than hydroxide, that should be an acidic solution. More hydroxide instead of H3O plus, that should be a basic solution in that case. And a lot of times the way we talk about things being acidic or basic is that we'll talk about pH. And so when we talk about the pH scale or just pH in general, the way we calculate pH is we take the negative log of that hydronium cation concentration. So the negative log of our H3O plus concentration. And as a general note, anytime you see this lowercase p in front of something, usually what you're doing is then taking the negative log of the thing that comes right after it. So if you see like pKa, if you went back a couple of slides to where I had the Ka values, you probably also saw a column that had pKa values. pKa is just the negative log of Ka. And so that just kind of gives you an idea of like when you see this lowercase p in different times this semester, that's kind of what it's always telling you. You're taking the negative log of kind of what comes after it. Now, couple of quick notes then on what the pH is really telling us. A pH of 7 is actually going to be a neutral pH. pH bigger than 7 actually means we're going to have a basic solution, because since this is a negative log, the bigger our H3O plus concentration gets, pH is actually going to go down. And now I think one thing I will point out, and just something to kind of keep in mind, I know this scale only goes from like 0 to about 14 roughly in terms of like an acidic pH to a basic, but you can actually go beyond those. You can have a pH higher than 14, you can have a pH that's actually negative if your concentration is high enough. So for instance, if you have HCl and it's 4 molar instead of 1, it's going to be a negative pH, and that's okay. Don't get kind of freaked out if that happens. That is something that's perfectly possible. We usually don't have concentrations so high for a lot of acids when we're doing things in lab that we have a negative pH, but it is something that can happen, so just do kind of be aware of that. But in terms of what we'll be looking at this week, if you do everything right in the lab this week, hopefully what you'll see is kind of starting pHs for your different solutions that should be slightly on the acidic side and getting more acidic for kind of each of the measurements that you make for your different trials that you should have put together. And so that gets us kind of into the experiment that we are going to be doing this week. What you're going to be doing is you're going to be taking an unknown weak acid and kind of say in quotes unknown, because we tell you in the lab and you'll see on the bottles it is going to be acetic acid in particular we're looking at. You can kind of use that to help you as you're going through and doing the calculations to compare. But we're going to be looking at this weak acid. We're going to react it with sodium hydroxide, and we're going to mix a little bit of water with it as well. And the general strategy here is that when you have an acid and a base like sodium hydroxide, is you're going to get a neutralization reaction. And this is something we'll be looking at a lot in kind of the next couple chapters as we talk more about neutralization reactions. But the main important thing about them is that they have an enormous equilibrium constant, which means that any neutralization basically goes to completion. So however much acid you have, if you add a little bit of base, all of that base is going to react till the base is gone, and then you only have like however much of your extra acid that's basically left. That's kind of what we're doing for each of the different little wells that you're going to be setting up to measure pH in. And what we'll do is we're going to measure the pH of each of our different kind of solutions that we make, and if we know how much acid and how much sodium hydroxide and how much water was all added, we should be able to find all of our concentrations of all of our really reaction components that we need in order to calculate the equilibrium constant, our Ka value. Because again, that's our main goal of this experiment. So I'm going to show kind of how we can walk through that, right? And so if we know the moles of acid and base that are going to be present, which in the lab it's going to direct you like you're going to add so many milliliters of the acid that has a particular concentration. Same thing for the base. If you have a volume and a concentration, you can find the moles. And then what you're going to find is if you know that they're going to go to completion, react to completion when you mix these two things, your moles of acid that remain are simply going to be your moles of your acid minus your moles of base. Right? And we'll talk about probably in lecture something called the BCA table that will basically go through kind of a similar process. But really for lab and the way the CSE Pub has things set up, this is kind of how you're finding the moles of acid really at, and it will probably refer to this as the moles of acid at equilibrium. And again, I'll talk about in a minute why that's really the moles of acid at equilibrium. And once you know how many moles of acid are left after this kind of neutralization reaction, then what we're going to do is make an ice table, right? Because Ka, we talked about earlier, didn't have hydroxide anywhere in it. It was all about taking your weak acid, putting it in water, and seeing how much does it break apart. So what we're going to look at then is that we're going to look at the reaction. We have our weak acid. We're going to put it in water, make an H3O plus and A minus. I'm just making sample numbers up here. These are probably not going to be your actual concentrations. But let's say you have 1 molar of your acid to start out with. If for your base you added 0.50 or 0.5 molar of like your base, or if that was the actual concentration in your mixture, what should happen is all this A minus should be there because when your base reacts with your acid, it's basically converting your acid into its conjugate base. And so that's kind of one of the big things I think calculation, and I'll say this again hopefully so that it makes sense. This first reaction that happens here when the acid and base do their neutralization, that is where, like at the end of this neutralization is where these numbers are kind of coming from. So some of your acid that you started with reacted with the base, the sodium hydroxide, and that's what made this A minus. And so we have some amount of HA and some amount of A minus that are currently in our solution. And what we can do then to try and kind of set up our ice table is if these are our initial concentrations for our weak acid and its conjugate base, now we can try and figure out, all right, how much do these things change? Right, and we can actually then put our X's in here for how things change, right? It should go forward because there's no real H3O plus that should be there yet. And so now as we add X to the product side, minus X on the reactant side, since all our coefficients are 1 and we know it has to go forward since there is a 0 right here. Water, notice we don't care about because it is a pure liquid, right? Pure liquids and pure solids not going to show up in our equilibrium or ice tables now. And then what we get to here is at equilibrium, our concentration of our weak acid, we should have something minus X. For H3O plus, it's just X, and for our for our conjugate base, we'll have some concentration plus X. But what we're going to know is that if we assume X is going to be small, since really the Ka values we're going to be finding are going to be really tiny values, we expect a very small equilibrium constant if it is a weak acid. That means that these X values here, like the minus X and the plus X, these values are likely going to be so tiny, they're not going to change like the actual starting concentration of these things. And that's why for CSE Pub, the way you're going to kind of see it labeled is it'll talk about, well, what's your concentration of HA at equilibrium? And it's going to basically say that it's the same as whatever your concentration for your acid was that was remaining after this neutralization. Because it's assuming that whatever amount here does dissociate is so tiny it's not really going to change its real concentration. And it makes kind of the same assumption for A minus. This isn't the best assumption in the world, but again, if we have a weak acid, that really should be kind of how it's going to work. It's not going to dissociate enough to really change those values. And what we're going to end up doing, the math here isn't all that bad. We're not going to be solving for X, at least not in a normal sense with Ka, because we're looking to find our Ka value, right? So if we want to find Ka, remember, is going to be the H3O plus concentration times the A minus concentration divided by the HA concentration for all the equilibrium values. But we actually do have a way to find this X, and that's by getting the pH. So in lab, we're going to be measuring the pH of our solutions, and then using the pH, we can actually calculate the H3O plus concentration, which gives us our X value, and now we kind of have all the pieces that we need to calculate Ka. And so that's kind of how our calculation setup for everything is really going to be working. Now, the actual lab experiment portion with the pH probes, I'm just going to show you what they look like. There's a pH probe. This thing is going to be inside this little kind of clear bottle container. It just kind of slides in and out. You can kind of, if it's stuck, you just kind of twist it and it should be able to slide in and out pretty easily. But these containers should be mostly full, maybe like half or 2/3 full with a liquid in here. And that's because we need to keep these glass tips of these pH probes saturated. We don't want to let them sit out for a prolonged period of time in open air or not kind of saturated with moisture or some kind of solution around this glass tip right here. Because what will happen is if this glass tip gets too dry, it will actually crack, and that will break the pH probe. And so do be kind of cautious of that. While you're doing the experiment, it's not a big deal because it doesn't really take that long to make our measurements. But when you're done, make sure that your actual pH probe, put it back in these containers, make sure this thing's relatively full with the liquid inside so that this probe is going to be submerged in the liquid, and so it stays wet and it's not going to kind of dry out and break over time. Now, in terms of what you're going to see, you hook up your pH probe to your LabQuest. You should see a screen here where it's measuring the pH. And I'm just going to walk you very briefly through kind of the calibration process. If you actually click the red background right here, it's going to give you kind of a quick menu option. And you can actually then select Calibrate to calibrate your probe. And what you're going to have is in lab, we're going to have a couple different what we call buffer solutions. If you don't know that term, it's not that big a deal. We'll be getting into that kind of in the next week or two. But those buffer solutions are an exact pH as far as how they've been created. And so one will be a pH 4 solution, one will be a pH 7. They'll be labeled, they'll be colored so you can kind of identify them. And what you'll do is after you hit kind of and select Calibrate, you're going to get an option here where if you select Calibrate now, then you're going to get an option to basically input kind of, all right, it's going to tell you like, it's going to give you kind of actually a voltage reading. And then you're going to have to basically tell it this is the pH of what it's currently been put in. And then you'll tell it to keep and do kind of the same thing a second time. And what you'll do that second time is you're actually then going to enter you're going to take it out of that solution that you told it it was a certain pH, and then you're going to put it in the second solution and do the exact same thing. So after you've gone Calibrate, tell Calibrate now, you're going to put your probe in one of your two buffer solutions. Doesn't matter the order. You can put it in the pH 4 one first or the 7. You're going to put it, say, in the pH 4 solution, and then tell it to keep that value, and then it's going to have you put it in the pH 7 solution, do the same thing. The only thing you're going to want to be on the lookout for is between putting the pH 4 and pH 7 solutions and telling it to kind of keep those values, is that when you're using those probes, always between each measurement, always rinse it off. So like during your calibration, you're going to put it in like I said, you can do it at pH 4 or 7 first, doesn't matter. So let's say you put it in the pH 4 buffer solution first, take it out, wash the tip of your probe with water, just like with a squirt bottle, and you can use a beaker to kind of catch the water that you're squirting onto that tip, and then dry the tip with a Kim wipe. Specifically a Kim wipe, try not to use a paper towel. Kim wipes are specifically designed to try and not scratch some of those probes, whereas a paper towel might actually scratch some of those probes. So try to use a Kim wipe in that process, kind of keeping it dry, because you don't want a lot of water on your probe, because adding those little bits of water can change concentrations of things when you're going to measure, and that might throw off pH measurements. So just trying to avoid kind of some of those little things like that. And so dry off the probe. Once it's been kind of rinsed and dried, put it in the next buffer solution. So if you did the pH 4 buffer solution first, now put it in the pH 7, tell it that's a pH of 7, hit enter, and then you should be calibrated. And you're going to do the same thing basically between each measurement. Once you're calibrated, you're basically good to go to just measure all of your 5 solutions. Just between each of your 5 measurements, you're going to kind of put it into your solution, make your measurement, pull it out, rinse it off, dry it, and go to the next one and repeat. And just make sure you're kind of rinsing it off between each measurement. That's kind of the biggest thing as far as using the probes once they're calibrated. Then when you're done, when you have the pH of all 5 solutions that you need to measure the pH for, which actually goes extremely fast. It takes just a few minutes to get all those pH readings. What you're going to do, make sure you clean everything up. Like go ahead and rinse the probe off one last time, dry it, put it back in that clear bottle that I was pointing out before, and make sure that bottle is reasonably full so that that probe is going to stay wet. Right? We need to make sure that we need to keep those probes kind of wet so they're not going to dry out and crack and potentially break, and then we have to buy new probes because they aren't the cheapest thing, unfortunately, for us to buy. So we want to try and make sure we take care of those things so that they hopefully will last. If you do notice that the bottle you're supposed to store it in is close to empty, just let your instructor know we have extra solution to basically refill those bottles so that we can kind of store those things properly. But really, aside from that, there's not much else that we're doing in this lab. You're going to be working in the well plate, so you're making very tiny amounts of solution. It's just kind of like a small amount of acid, a small amount of base. Most of it's neutralized. So when you're actually done with everything, it can actually just all go down the sink this time. So there is no special waste cleanup that you have to really worry about. And so you can just make sure, like when you put it down the sink, just rinse it with some water, it should be perfectly fine to be able to go down the sink. Acetic acid, which is the acid we're using, is pretty much just kind of, it's what you see in vinegar. And so it's not really going to, like a small amount of it's kind of like pouring a little bit of vinegar down the sink. It's not really going to hurt much. So everything from this lab, like I said, easy kind of waste disposal, but it is more kind of just make sure you're kind of taking care of those pH probes so that we'll have them for later use. Past that, I think that cuts all the major points as far as things you probably need to know for this week's lab. This week's lab is one of our faster ones usually, so it is relatively short in kind of total time spent. But hopefully it's kind of giving a quick introduction. And there's a decent number of calculations you'll have to do for it, but I think it's a good introduction to doing a lot of the calculations we're going to be seeing for a lot of our acid-base chapter here that most of us are getting into.